Okay, so welcome to my lesson. My name is Mr. Johnson, and I'm here to talk to you about physics, forces, energy, and their effects. So I'm going to share my screen with you. One moment. We're going to have a look now at the lesson itself. So this is my lesson on forces, energy, and work, 20-minute lesson. Prior knowledge that you should have. So in the past, Key Stage 3, that's years 7, 8, and 9, what you should have been taught is that a force is a push or a pull, giving some examples of forces and their effects. Recall and describe the different energy stores with examples of each one. And finally, describe the law of conservation of energy and apply it to different energy transfers. By the end of this lesson, then, what you should be able to do is identify the types of forces that can transfer energy with examples. Describe how to calculate the work done to transfer energy and what is needed to do this. And finally, describe how to calculate the power of an appliance and also, again, what is needed to do this. So, objects can interact or affect each other by exerting forces on each other. For example, if you push down on the table pushes back on you. Another example, I want to make a football move, I kick it. But to kick it, my foot has to touch the ball to push the ball. I can't make a ball move without touching it. Second example, picking up a paperclip with a magnet. Now I can touch the paperclip with the magnet to pick it up, but actually I don't need to. If you've ever played with a magnet before, you know that you can bring it quite close, very, very close to the paperclip, and the paperclip seems to just sort of jump and attach itself to the magnet without any touch. These interactions cause energy to be transferred between the objects. In this case, we say that work has been done. So what we're talking about, well, we've got different types of forces based on whether they need to be touching, like my football, or whether they don't need to be touching, like, for example, the magnet and the paperclip. Contact forces are forces that act between two objects that are physically touching each other, or they're in contact with each other. Examples of this being a normal contact force. Now, this is one that most people don't get, but actually a normal contact force is a force that's a reaction force at right angles or at a normal to a surface. For example, the force on a table pushing back against a box that's pushing down on its surface. The contact force is, if you're sat in a seat, what's preventing you from falling through the seat. Your weight is acting downwards on the seat, but the seat is acting up against you to provide a force that prevents you from sinking through it. This is called a normal contact force. Tension. Tension's not just when you're feeling under pressure, but it's also in an object that's being stretched by two opposing forces. It's an example of a force that, for example, is found in a cable holding up a swing seat when you're sat in it. Or even if you look up at your light in your living room or your bedroom or wherever you're watching this video, it's the stretch that's in the cable that's holding the light bulb to the ceiling. Friction, air resistance, and water resistance. These are all forces that occur when two objects slide past and rub against each other. For example, a sledge going down a hill, the sledge is in contact with the ground, so the ground and the sledge are rubbing against each other, and you get heat generated through friction. Air resistance, when air particles are moving against an object that's moving through the air. For example, plane moving through the air. Water resistance, same thing, but instead of air particles, now we're talking about water particles moving and sliding past an object moving through it. Finally, upthrust. Now, this is a force that acts against the weight of an object on water. It's what keeps things afloat. So, for example, a boat has weight. You put it in water, the weight of the boat pushes down on the water, but the particles of water push back against the weight of the boat. This is why it floats. If the weight is heavier than the force that's pushing back, the upthrust from the water, then the boat sinks. But for all these forces to work, they have to be in contact with an object. These are different to non-contact forces. These are forces that can act between two objects that are not touching each other, i.e. not in contact. Examples of these are the magnetic force, which is a force we came across before, experienced by any magnetic material in a magnetic field. For example, paper clips sticking to a magnet through a piece of paper. It's not actually touching the magnet, but it's still in the field of it, so it can feel its force. An electrostatic force, a force experienced by any charged particle in an electric field. For example, you rub a balloon against a wall, against a hair or a particularly woolly jumper, it'll stick to a wall. Or if you're really cruel and you've got a baby sister or a baby brother with long hair, then you can wave the balloon over their hair and you can watch their hair rise to meet the balloon. It doesn't have to touch their hair, it just has to be near to it and it will attract it. Finally, gravitational force. This is a force experienced by any mass in a gravitational field. Different masses are attracted to each other by gravitational force. For example, a meteor falling to Earth. Earth has mass, so does the meteor. There's a gravitational force between them, and one falls towards the other. So that's identify the types of forces that can transfer energy with some examples, classifying them as contact and non-contact. The next part of this is describe how to calculate the work done to transfer energy and what's needed to do this. To understand this, we need to know what energy and work done are and how they relate to each other. Going back a bit to what you've been taught in the past, the law of conservation of energy states, energy cannot be created or destroyed, just transferred from one energy store to another. Now, it seems very simple, but it's actually quite important to understand this. It means energy just can't be magicked out of nowhere and it doesn't just disappear. All that happens is the energy from one place moves to the energy in another store. So for example, if I turn on a kettle, going back to what we've taught in the past, I apply electrical energy through the cables to the heating element, which is then transferred to the heat energy store of the water. So what energy I put in is the same as the energy I put out. When work is done then, energy is transferred from one store to another. So the act of transferring energy is the same as doing work against whatever it is that you're doing. This then leads us to the idea that work done is equal to energy transferred. And this is important and it becomes obvious why later on. When a force causes a body to move then, work is being done by the force on the object. So, person at the top there pushes the box. When they apply the force to the box moves. This means that they're transferring kinetic energy to the kinetic energy store of the box. The further the box moves, the more energy the person is transferring, so the more work they're doing. I say that they are doing more work to move the box, the further along they push it. This means that distance is one of the factors that can affect the work done. To lift the weight, the person has to work or pull, apply force against the weight. They're lifting upwards. If they lift it up, they transfer strain or elastic energy from their muscles to the gravitational energy store of the weights. So energy has been transferred. The more force they use, the more energy they have to transfer. We say they're doing more work against the weight. So this means that force is also one of the factors that affect the work done. So we can see from the previous examples that the factors that affect the amount of work done are how much force are used or is used, and how far an object moves in a straight line due to that force. This leads us to the equation then for calculating work done. Work done equals force times distance moved in a direction. The symbols for this, work done, E, because work done is the same as energy transferred, so it uses the symbol E to remind us of that. Force, F, distance moved, D, where energy and work done are both measured in joules, force in newtons, and distance in meters. So let's have a look at a couple of examples. Example 1. Amy pushes a book 5 meters along the table with a force of 5 newtons. She gets tired and decides to call it a day. How much work did she do? Notice that I have made a point of highlighting in different colours the two pieces of information that I've got here. She pushes a book 5 metres in red along the table with a force of 5 newtons. So I have a distance and a force. How much work did she do? Well, first thing I do is put in the equation. You should always, for best practice, do this in any exam because it shows the examiner that you're not just guessing, and if you make a mistake along the way, you will still score for some of these. Then I place the numbers into the correct places under their placeholder. The force is 5 newtons, so I placed it under force. Distance moved is 5 meters, so I placed that under there. You might say, well, it doesn't matter at the moment because they're both the same thing, but it's good practice to do it the right way around in case the numbers are different. This gives us a work done of 25 Newton meters or 25 joules because work done is the same as energy and they both have the same unit. Let's try a second example then. Ronnie does 200 joules of work by pushing a wheelbarrow with a force of 50 newtons. How far did he push it? What type of energy did the wheelbarrow gain? In this case, the question asks us slightly differently to use this equation. Now I'm not looking for the work done, but I have the work done and the force, and I'm looking for the distance that it was moved through. This means I need to rearrange the equation. Now, I'm not going to go through the steps for rearrangement, but if we take the equation, work done is force times distance moved, and we rearrange it to make D the subject, then distance is equal to work done divided by the force applied. Now that I've wrote that down, I'm going to place my values in the correct place under the equation. So work done is 200 joules, force is 50 newtons, so 200 joules divided by 50. And then you can do it in your head, you can do it on a calculator, it doesn't matter in science because we're a calculator-friendly subject, but the answer is 4 meters. Now the second part of this question, what type of energy did the wheelbarrow gain? He's pushing the wheelbarrow, which means that the energy is being transferred into the movement energy of the wheelbarrow. And as you may be aware, should be aware, movement energy is the kinetic energy store. So the barrow gains kinetic energy. Final example. Julian cuddles his cat and lifts it 1.5 meters in the air. If he did 75 joules of work, how much force did he use? Now again, it's not asking us for the work done, it's telling us how much work has been done. Now it's asking us to rearrange the equation to calculate the force. Going through it, I write down the equation as is, and then rearrange it to make F the subject, which gives us force equals work done divided by the distance. Now that I've got that in, I'll put my numbers in the place of the equation placeholders. So the work done is 75 joules divided by a distance of 1.5 meters. Do it on a calculator, and it turns out as 50 newtons of force are applied. That's our second point. Describe how to calculate the work done to transfer energy and what is needed to do this. Our final outcome, describe how to calculate the power of an appliance and what is needed to do this. Power and work. Earlier on, when we were talking through the energy done, work done section, we came across the idea that work done is equal to the energy transferred. The rate at which energy is transferred is called the power. Rate is a word that most people don't tend to get. They confuse it with speed, and it is a kind of speed if you like. It's how fast something changes per second. So the rate at which energy transferred per second is the power. Power is measured in a unit called watts. You may have seen this before on the rating for a light bulb packet, for example. Old style light bulbs used to be measured in 14, 60 and 100 watt bulbs. The newer style ones tend to be 9 and I think 11 and 15. In short, power is the amount of work done or transferred, energy transferred, every second, and it's measured in watts. Power and work done then. Going back to our earlier example of the man pushing the box, the person pushes the box. The box moves. This transfers kinetic energy to the box because the box has moved. We are saying that they are doing work to move the box. We've come across this idea before. But if they push it further than before in the same time, then they are transferring more energy than before. This might be if they were pushing this box with the same force down a hill compared to before, so they push it over a greater distance in the same amount of time as it would before. This means they are pushing with more power. The person has to do work against the weight. The more force they use, the more energy they transfer, the faster the weight rises. We are saying that they are doing more work against the weight. If they do this in the same time as before, then they are lifting with more power. So from the previous examples, the factors that affect the power are 1, how much work is done or energy is being transferred, and 2, how much time it takes the work to be done or the energy to be transferred. This leads us to the equation for calculating power, which is power equals work done divided by time taken. In symbols, power has the symbol P. Again, work done is the same as energy transferred, so we use the symbol E, divided by the time, and time is always given the small symbol T. Power is measured in watts, energy and work done in joules, and time in seconds. So let's take a look at a couple of quick examples on this one. What is the power rating of a light bulb that transfers 120 joules of energy in just 2 seconds? Well, the first thing is to place down the equation. Power equals work done divided by time taken. Then I put my quantities in the places where I can fill them. I've got a work done, which is 120 joules of energy transferred, and a time taken of 2 seconds. Note that the question doesn't say what the work done is, but it says it transfers 120 joules of energy. This is where that rule, work done equals energy transferred, comes in handy. So I've got 120 joules divided by 2, which means that the total power of the light bulb is 60 joules per second, or 60 watts. Second example, Georgia runs up the stairs at home in 5 seconds. If her power rating was 200,000 watts, how much energy did she transfer? Again now, this question is asking not for the power, but for how much energy she transferred, which we know is equal to the work done. So in this case, we're going to use the same equation, power equals work done divided by time taken, but we're going to rearrange it to make work done the subject. Work done equals power times time. That means that I've got 200,000 watts of power times 5 seconds. So the work done is 1 million joules, or if you like, 1 megajoule. Last example, example 3. An 800 watt rated hairdryer transfers 48,000 joules while Sima dries her hair. How long did she use the hairdryer for? Again, we've got an energy transfer of 48,000 joules, which is the same as the work done, and we've got a power rating of 800 watts. We're being asked to find the time that she used the hairdryer for. Power equals work done divided by time taken, but now I'm rearranging it to make T the subject. So time is work done divided by the power. 48,000 joules divided by 800 watts, and the time is 60, and because it's always measured in seconds, it's 60 seconds. Be careful of this, because in the exam they could ask you to give the time in minutes or in hours, in which case you have to be able to convert seconds to minutes and hours, which is straightforward enough. That's our final outcome. Describe how to calculate the power of an appliance and what is needed to do this. I hope you enjoyed this lesson. Thank you very much for watching, and see you next time.